Hello and welcome to the Women in Machine Learning and Data Science meetup, hosted today at lunch at Zendesk. A quick shout out, we are looking for future speakers, so if you have a talk you'd like to give or you know a particularly good speaker, please come have a chat with myself or Fiona, who's going to stand up over there. This lady, who is another WIML DS organizer, and we will point you in the direction to submit that nomination. So today we have two fantastic speakers who have various experience in machine learning, AI, and science, and I'm going to read off their notes. So our first speaker today will be Lily Martin. She's a data science intern in the digital innovation team at the National Australian Bank, and she is part of a major natural language machine learning project to understand what customers are saying and feeling. So today she's going to be doing a bit of a deep dive into natural language processing for us. Then we'll have a short break, and our second talk will be Dr. Ruth Pearson. She has a background in physics, and I added the doctor, she didn't, by the way. She has a background in physics, statistical and computational methods to study the early universe. And she is going to be talking to us today about blood donation practices. She has a special interest in the interface of AI, human, and veterinary medicine. So it'll be very interesting to see how those topics come together. So please welcome first, Lily Martin.
Cool. So before I get started, I would like to acknowledge the Wurundjeri people, the traditional owners of the land in which we are gathered and meeting on today, and pay my respects to both elders past and present. Cool. So as Arwen mentioned, my name is Lily Martin. I'm currently working at NAB in the Digital Insights and Analytics Department. And today I'll be talking about NLP, or natural language processing. I designed this talk to be for someone who has no understanding of machine learning or even data science, and could hopefully gain some insight into the NLP world. With that said, let's get started. So what is NLP? So NLP is a branch of, let me start again. That's the contents for today. So first I'll talk about what NLP is, then I'll talk about how NLP is used in the world around us, and then I'll get into a more technical aspect of this, in which we're going to build a basic NLP pipeline, and I'm going to talk about some of the tools you can use to use within this pipeline. So, try that again. What is NLP? So NLP is a branch of AI. I really like this quote. So natural language processing employs computational techniques for the purposes of learning, understanding, and producing human language content. It started generally with a rules-based approach, so writing all the rules that underpin a language, and it naturally evolved. So naturally involved languages are quite hard to understand and quite hard to capture in this rules-based method. That's where neural networks sort of have stepped in. We're by no means building human-esque AIs ready to take over the world, but we're getting pretty close. So how is NLP used in the world around us? So spell check is an example of NLP, autocomplete, text-to-speech, and things like Siri and Alexa. It's also used in things like chatbots and sentiment analysis, spam filters, and also detecting fake news. And some of the cooler ones I found while doing this, while researching for this speech, were that it's helping actually give the power of speech to people living with disability. It's also converting sign language into text. Google Translate is actually an example of NLP. And also the recognition and prediction of diseases using electronic health records and patient reporting. So with that said, NLP is all around us, so we can get into the more technical side of things. So in the next section, I'm going to walk you through a basic NLP pipeline. And the best way to understand any data science pipeline is to answer a question. So let's say we're all part of a company. And we want to know, what do customers actually want from our company? So we can go about this a number of ways. We can look at the data and we can say customers are buying X, Y, and Z, therefore they must like this. However, looking at text data gives you a far deeper insight into what the customer actually wants. A way you might accomplish this is through surveying your customer base. So that's easy and surveying and reading those surveys. So that's easy when you have about 100 customers or even 1,000. So what happens when you have 6 million customers, or you're a massive business like Facebook and you have 2.7 billion customers? That's where NLP steps in. So let's have a look at some angles we can take on this question. The first is we can understand the sentiment of what the customers are saying. And I like to say it's quantifying the general vibe of the sentence. So a way to look at that is whether it's positive, negative, or neutral. So for instance, I love the new app. It's pretty positive. This app sucks is obviously negative. And where can I download the app is an example of like a neutral sentence. You can also look at categorical analysis. So this is what people are talking about. So if we go back to those 3 sentences, we can see that each one of these people is talking about the category app. And then you can look at things like topic modeling, which is a way to surface new things that people are talking about. So what do I mean by that? So if you're introduced to a 4th sentence here, the chair is great for my back. So our computer will go, hey, that doesn't fit into this category that we've predefined. And the topic modeling will surface a new category that we can then label as chair or whatever you want back potentially. So now we've had a bit of a talk about what NLP is and some of the ways we can approach an NLP question. Let's look at a basic NLP pipeline. So like all ML modeling pipelines, it sort of has 5 distinct steps. So you've got sourcing, pre-processing, feature engineering, modeling, and deployment. So let's look at sourcing. So text data is great. It's all around us. So at the moment, I'm actually giving you text data by talking. You can get text data from the internet, survey data, complaints data, which we're familiar at NAB, social media data, virtual assistant data, reviews, books, really anything that has any sort of language, so anything that's spoken or written. Ways to collect that will depend on what data you're collecting. So you could be transcribing what I'm writing now, what I'm saying now rather. You could scrape the web. You could use more advanced techniques like voice to text. Even computer vision can be used to analyze text data, survey forms, online databases. However, when you're answering a company-specific question, it is likely that whatever company you work for will have will collect some sort of text data. So that's sort of your first place to start. So text data is like all data. It needs to be cleaned to a degree. So I thought I'd walk you through some of the basic tools we use to clean text data. This is not a complete list, and it's only going to be a few because really you can do anything. However, I thought I'd talk you through some of the words that if you were to undertake an NLP project, you might come across. So stemming is a rudimentary rules-based system removing the suffixes from words. So for instance, you've got rocks becomes rock, singing becomes sing, happily becomes happy with an I. Lemmatization is the more advanced process of doing it, where it takes a word and reduces it to its base lemma, or like the root of the word. So rocks becomes rock. It also handles the cases that stemming wouldn't handle, like corpora and corpus, where the pluralized version is different from the singular version. And also things like good and better. So better is actually the lemma of good. So this is all language principles here. Stop words, the removal of stop words is a common practice in cleaning text data. So stop words are commonly used words. For instance, the, in, us, I, an. Basically, the removal of stop words allows for a smaller data set. It also allows for a cleaner one. And what I mean by cleaner is that because these words are repeated a number of times, your computer could mistakenly think that these are important words. Whereas if you remove them from a sentence, the sentence still maintains its underlying, I guess, nuances. For instance, like I love data science. If you remove I, it just becomes love data science, which means that it's still expressing a positive sentiment towards data science. Sort of a final step that people do take is noise removal. So in text data, that means removing things like URLs, hashtags. If you're web scraping, it might mean removing punctuation. And actually, I've looked at some places that talk about removing industry-specific words. However, when you're building out your own model and you're using industry-specific, and you're building something for your company, removal of industry-specific words doesn't actually make a whole lot of sense. Neither does the removal of hashtags and punctuation. So when you're doing sentiment analysis, hashtags and punctuations can actually add to the sentence. So an exclamation mark might express increased anger or increased happiness, and a hashtag might actually give you more information about what the person's trying to say. So for our problem, we might not even want to remove any of this data. So now we have a nice clean data set. Unfortunately for us, computers can't read words, but they're really great with numbers. So we need to find a way to convert words into numbers. So that's called vectorization. And there are a number of ways to do this. I'm going to walk you through the most basic way, and then I'll talk about two more complicated ways. So the first is through one-hot encoding or bag of words. So let's say if I have two sentences here. So my name is Lily and I love doing data science. And two, data science is the best. If I was to take every single unique word in those two sentences and throw them together, I'd end up with what's called a bag of words, or a corpora, or a lexicon, or a dictionary, depending how you look at it. So now if I was to make each one of those words a column value and each sentence a row value, and every time a word appeared in the sentence, I gave that column value a 1, this is what it would look like. And that's vectorizing in a nutshell. So you can see anytime my appears, you get a 1, and so on. So there are two immediate problems with this method. The first is there are going to be a lot of zeros. So if I was to introduce a third sentence that was just my name is Lily, you can see that I've only filled the first 4 columns and the additional remaining 8 columns are not filled. Another problem is the size of your data set. So this is only with 3 sentences. Can you imagine, and we already have 12 columns. Can you imagine what would happen if we had 1,000 rows? The third problem, and one that is not immediately clear from this example, is that this lacks a lot of context doing it this way. And I'll talk more about what that means later. So there's been a few attempts to remedy these problems. And the first is, the most common is utilising word embedding. So the technical definition for word embedding is the mathematical embedding from a space with many dimensions per word to a continuous vector space with a much lower dimension, which is not the world's greatest definition or easiest to understand. But in essence, word embeddings attempt to capture the meaning of the word as well as their context and capture that inner vector. Probably the best way to understand it is, again, through a couple of examples. So here we have 3 examples on the page. So we have man and king, queen and woman. As you can see, king and man are close together, queen and woman are close together, and king and queen are associated and man and woman are associated. This could also work for something like verb tense, where you've got current tense like walking and swimming being close together, and walked and swam being close together, and also walking connected to walk and swimming connected to swam. And the third example I have here is that you've got countries on one side and their associated capital city on the other. And they're actually sort of ordered about how you go around the earth. So there are a number of different ways that people do word embedding. So Word2Vec, Doc2Vec, Glove, USE, Elmo, and BERT. Yes, those are the names. I'm only going to talk about 2 today, just for sake of time, and also because these are the 2 that I'm most familiar with. So the first is Universal Sentence Encoder. So Universal Sentence Encoder works by taking sentences and applying a vector and pushing those sentences out into a 512-dimensional space, which we can't visualize, but a computer can. So words and sentences that are similar are then treated the same. For example, let's look at these 3 sentences. So this product is great. I had a fantastic time using this product, and I do not like the colour blue. So the first 2 are obviously expressing positive sentiment about a product, whereas the last is expressing a negative sentiment about the colour blue. If we use USE, we ended up with a data frame with 3 rows and 512 columns. If we then apply something like a similarity equation, for instance, cosine similarity, we can have a look at how similar these words are. So you can see from 1 and 2, they're quite similar, whereas 1 and 3 are not similar at all, and 2 and 3 are not similar at all. The second embedding method I'd like to talk about today is BERT. So BERT is bidirectional encoder representations for transformers. And so it really attempts to answer the question about context. So what do I mean by context? So you've got two sentences here. He wound the clock, and her mother's scorn left a wound that would never heal. Now, these are called heteronyms in that they're spelt the same, but they're pronounced differently and they have vastly different meanings. BERT tries to look at the sentence as a whole and understand those words. So common methods to understand sentences or sentence structure, you have forward reading and backwards reading. BERT looks holistically at the sentence. And BERT is trained to predict the next word. So what it does is it goes along looks at a sentence, removes a random word, and then tries to predict it. That's BERT's sort of decoding step. But how can we use BERT for our sentiment or categorical analysis? So, if this works. BERT works as an encoder and a decoder. So it encodes the sentences and then, like we were talking about with the universal sentence encoder, and then decodes them to guess the next word in the sentence. So to get the best decoder, you need the best encoder. If our sentiment model or our categorical model is the decoding portion of our pipeline, BERT could be used as our encoding part. The benefits of BERT is that it was trained on a large amount of data because it was developed by Google. So it already knows a lot about our language. And so that means you need less training data. Other things is that BERT has performed insanely well comparatively to other models. So we have our data, we have our clean data set, we've embedded it using either BERT or USE. And what do we do next? Well, we finally get modeling. So before I use an example of a model, I just wanted to touch briefly on some off-the-shelf Python packages that are available to complete some of the modeling tasks. So first you have NLTK, which is a natural language toolkit, which has a large pre-labeled corpus. It can do some categorical analysis, and it also contains some pre-built models like some naive bias classifiers. TextBlog piggybacks off the NLTK library. It can do sentiment analysis, language translation, some classification, and spell correction. GenSim is purely used for topic modeling. And Spacey is more the sort of productionalized answer to NLTK and contains some pre-trained neural nets that can do things like split sentences, for example. However, because we're using industry-specific data, we sort of end up having to build our own model and train our own model. So, as you all know, building models can really take any flavor you want. You can sort of go from a simple linear regression, if that's what you're comfortable using, to a neural net with like 50 bazillion layers, if that's what you desire. So it can be as simple as complex as you'd like it to be. So for simplicity's sake, let's build just a general multi-layer model in Keras. So Keras is a deep learning framework that can support our model. The best part about Keras is its usability. So they say on the website, Keras is an API designed for human beings and not machines. And what does it mean by that? Well, if you look at the code below, you can see that we've defined our model at the start, find what type of model we're having at the start. And then here we've got simply 2 layers. Well, it's actually 3. So you have your input layer and 2 middle layers. And then you're compiling your model and you're good to go. The best part about Keras is it's easy to read and it's simple to use. So how does a model fit into Keras? So we can use something like a convolutional neural net. So CNNs were originally developed for use for 2D images. So they basically take a feature, wind it up to a larger feature, and then eventually can identify an image. They can also be used on 1D data sets like our text data. Maths behind the CNN is well beyond the scope of this talk. However, what we can do is have a look at the image above and input those CNN layers into a Keras model. So here we have our embedding layer. So this could be replaced with something like BERT or USE. We have our convolutional layer, we have our pooling layer, we have our fully connected layers, and then we've got our compiler. And there we have our model. So in less than 10 lines of code, our model is ready to go. So now we've trained our model, we're running data through it, everything's looking great, and we're at the final hurdle, which is deployment. So deployment can take many forms depending on what company you work for. And so I won't get into too many specifics about deployment. However, these are some questions that are interesting to ask yourself. So where do we house the results? Are they housed on-prem? Are they housed in the cloud? What needs to access them? And by that, do I mean, does something like Tableau need to access them, or are they simply in Excel? How are they going to be accessed? Are they in JSON format? Can they be accessed through SQL searches? Timing, so when does it need to be accessed? And that will impact storage. And who needs access? Is it just your technical team? Is it your CEO? It will really vary immensely. So we've finished our pipeline. We've sourced data and we've learnt that there is so much text data around us and it can really come from anywhere depending on the question you want to answer. We've learnt a bit about pre-processing and understood that pre-processing will really largely depend on the question you're trying to answer. We've looked at feature engineering for text data, which is actually mostly just embedding and vectorizing the words, and which step you take will depend on a lot of things like computational size, time, what have you. Modeling, we've had a look at how a model would just slot in to this pipeline, and we've answered some questions, or we've had a look at some of the questions about deployment. So that's all I've got for you guys today. I wanted to thank my NAD team, some of who are here today, for coming along this NLP journey with me. It's not one that I took solo. And also all of you for coming out today. Thank you. Are we doing questions now or at the end? Okay, cool. At the back. Bias. Yeah. Correct. So it was something when we went down the NLP route that we were always aware of. And I guess it's hard. It's one of those things that sort of you can only be aware of it and try your best to avoid biases. And so when we tagged data for a project I was part of, we were sitting in a massive room where there was a lot of us. It wasn't just someone solely tagging. And any sort of questions we had were met with the team. So that's really how we tried to overcome bias, by having a lot of different people involved. Mm-hmm. Mm. Correct, yeah. Yes. Cool. Any other questions? Yeah, Ruth. Mm-hmm. Yeah. Yeah, so stemming sort of has been largely replaced by lemmatization. So lemmatization, what I had in my notes but did not say, lemmatization would handle cases like that. It would actually, it would convert happily to happy. Stemming is really just sort of a rudimentary starting point. It can only recognise the fact that it's got an ly on the end, and that's a suffix, and it can chop that off. Yeah. Sarcasm's a hard one. So humans aren't great with sarcasm either. and sarcasm's very culturally specific. We tried, when we looked at text data, to look at it very rawly and tried to read it in quite a neutral voice, because we did find ourselves kind of doing these things like, well, if I read it like this, it sounds like that. And so we tried to keep it as neutral as possible. However, things like, for instance, voice-to-text data, that could be a way to capture things like sarcasm. Like, you could say they said it in a sarcastic manner, but then how do you define a sarcastic manner? It becomes very complicated. Yeah. 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 I used my team. And Yeah, so what we did was we had a large amount of data. So we split it into groups of, I think about 1,000 rows. And then I just sent it to the people. We had a tagging party. We all sat in a room, had chips, beer. It was great. And so everyone got 1,000 rows and it had a sentiment column. So we did sentiment and categorical analysis. It had a sentiment column and then categorical columns. So we just sat around and we tagged. We then used some rules-based approaches to get sort of some really easy low-hanging fruit. For instance, things that were highly negative, like swear words were an example. But yeah, so it's interesting. Tagging's difficult. Yeah. So like with anything, so you measure it against, you've measured like the F1 score against your trained and testing data. So with any sort of model that you build, you'll have a training set and a testing set, and then you measure how well your testing set performs comparatively to your trainings, what you trained it on, basically. Yeah, so it is something we're actually looking into at the moment. So ways to do that are through like anomaly detection methods. That's generally, but it's something we're currently exploring and something I'm not too familiar with at this current stage. Yeah. I'll go to someone new. And then I'll go. Yeah. Yeah. Go back to it. Yeah, so I had to think about this, and I think it's just a rounding error, honestly. I'm not entirely sure. This was a 10-minute thing I just threw up in Jupyter. It didn't actually come from any work that I've done. But yeah, so I did actually look at that and go, should I just like make it one and just move on with my life? No, I think it's honestly just, I think if it allowed for more decimal places, you'd find that this one would be huge as well. Yeah. Mm-hmm. Having it at one more. So using BERT just fully. Yeah, so I wouldn't know how to do that. Is probably, I haven't seen any methods where they have done that. It's mostly encoding is normally the first step that you would take. So the way USE and BERT work are it's very complex. And so they really try to really drill down into those nuances. And they're also, BERT at least is bilingual, or whatever, multilingual. So it's across different, so it understands quite a lot about language in general. And so so BERT's probably would be the closest you'd get to feeding raw text data in and getting a result out, because it does that encoding step as part of the process. Yeah. 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 So we use PII scrubbing. So we basically look for things like names, addresses, phone numbers, credit card numbers, you'll see, because of it NAB. And we have a scrubber that goes through and finds those and removes them. And I believe it's a rules-based scrubber. Yeah. 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 So that's where sort of a human tagging is great, because if you fed that to a pre-trained model, it would probably be like, that's negative. But if we saw it in tagging, we'd be able to be like, that's actually positive. You very rarely find in one sentence a positive and negative sentence. I haven't seen it. That's for our project, we actually split into sentences, because you'll definitely find in paragraphs, it'll start positive, like, I've always had a great experience at your company, but X, Y, and Z has happened. So you'll find that, you can split by sentences and by words like but, and that breaks it up easily. Yeah. Any last questions? Yep. No? And sorry, what was the second one? BERT. So TF-IDF doesn't actually take into account the context. It actually just takes into account how many times the word occurs. So for those who don't know, TF-IDF is term frequency inverse document frequency. So basically what it does is it goes, how often does this word occur in the documents that you have? And then it captures how important that word is. So for instance, the word the is not important, but appears a lot of times. So it decreases the number on the. So with that, you wouldn't actually be able to get any context. It doesn't capture that. Whereas something like a vector space tries to map context to the word or to the sentence that you're using. So yeah, so that's probably the main difference. TF-IDF is just a mathematical neural nets, but it's quite a simple mathematical equation, whereas BERT and USE and neural networks that have been trained on models, trained on data, sorry, yeah. Yep, no, sorry. So we're currently in the phase of just doing some final stages of it. So we're looking really, without getting too far into it, we're really trying to understand, so customers fill out these forms, they give them to us and they give them a score. And the score will be at odds with what the customer is saying. And so that's really what we were trying to map or trying to change that difference. And so we are currently working towards having a deliverable outcome, but we've still got some final little tweaks to make. Yeah, cool. I think I'll pass on to Ruth. Thank you.
Now would be a good time to get up and get some more pizza if you haven't had any lunch yet. Otherwise, we will welcome our next speaker, Dr. Ruth, who will be discussing blood donation practices. Yeah.
That one again?
We swapped.
Oh, no, that, oh yeah.
Yeah. I actually have it.
Is this gonna do stuff? What's this for? Like, does this need to be on me?
It's a microphone because you can speak out.
At it, okay, no problem. Yeah, that's fine. What, change its name? Oops. Yeah, thanks for letting me know. It's what's it called?
Oh, yeah. Yeah. Blood does no, that's
Okay, folks, if everyone's got enough pizza, I think I will begin. I'd just like to echo Lily's acknowledgement of the traditional owners of the land and recognise that we're meeting on stolen land, and this always was and always will be Aboriginal land. I'm going to talk to you today about a project I did while I was working at a place called the Burnett Institute, and it has to do with blood donation practices amongst Australian people who inject drugs. However, before I get into the details of that, I did just want to tell you about this program, which some of you might be interested in, the Young Women Leaders in AI. I'm a mentor and a program advisor for this, and it's a 12-month journey for 16 to 26-year-olds. So you can apply to be a part of it, and what it is it kicks off in Queensland on the Gold Coast with a 6-day residential program. This will be the third in 2020. I've been a part of 2 so far. And so the idea of the whole program is to encourage and engage young women to become the next leaders in the AI space. And so after that program, you get ongoing mentorship. The applications are closing quite soon for the 2020. They're closing on the 30th of November. So please have a look at their website. I've put the link up here, womeninai.com.au. You can read all about it and you can apply. It's completely free, but it unfortunately doesn't include transport and accommodation up to Queensland. Last time there were some Victorian participants. Fatia at the back there took part last year. If you just want to give a wave, if you have any questions, you can either ask about how it was or ask me any questions and I'll do my best to answer. So just wanted to let you know about that program. That might be of interest to some of you. So from 2016 to 2018, I was working at the Burnett Institute in Melbourne. It's in Paran, and it's a medical research institute, so it has a lot of academic research as well as a lot of practical programs on the ground. I was an analyst there. And so while I was there, one thing I did was take part in this investigation into blood donation practices among Australian people who inject drugs. So that was an independent review commissioned by the Australian Red Cross Blood Service. So the Red Cross Blood Service wanted to know if the rules they have around people who have injected drugs donating blood were fair and reasonable. And so they commissioned the Burnett Institute to lead that review, and I was lucky enough to be brought along on the data science side. I chose to talk about it because it's quite a simple model. I'll probably only talk for about 20 minutes, but it's really interesting because it kind of wraps up nicely because it's something that happened in the past. So I've got answers about the results, which is quite rare for me when I'm giving talks. And also because it really demonstrates the power of having the right data and engaging the right organizations. And I'm proud to have been part of work which changed policy in Australia because we found that it was discriminatory policy. So you can see the key stakeholders here, and I even just looking at the stakeholders list, I thought it was really interesting because there's a lot of academic institutions, so UNSW, St Vincent's Hospital, that were involved in this review. They're obviously on the research side, but also the Haemophilia Foundation Australia, because their interest is that people with haemophilia are going to be needing a lot of blood transfusions. So they have an interest in being part of this review, but then also the National Drug and Alcohol Research Centre and the Australian Injecting and Illicit Drug Users Leads. So the people that the policy is currently affecting and will affect if it's changing. So it's really cool to be a part of that. And the goal was to examine the injecting drug use deferral criteria and recommend how these exclusions or deferrals from donations should be structured. So it's standard practice worldwide to exclude certain specific risk groups from donating blood. So, for example, people might get excluded or deferred from donating blood if they're considered to be part of groups that present higher risk of bloodborne infections and viruses and things like that. So men who have sex with men, sex workers, injecting drug users, these are groups that are often excluded from donating blood in many different places. So I am, in fact, also excluded from donating blood in Australia because I lived in the UK. You might be as well, because I lived in the UK in the 90s when mad cow disease was around. And so there's this risk that it's being hard in my body. I think it lives in your brain. So I'm not allowed to give blood. When you have these policies, the blood bank needs to make sure that they're fair and reasonable. And so their policies on people who inject drugs hadn't been updated since the 80s. And so the main risk is that someone has an infection such as HIV or hepatitis C, and that gets passed on through the blood. So my task was the data science task, and the question was, what would the additional risk to the blood supply be if the deferral period was changed from lifetime to 1 or 5 years? So the rule was that if a person in Australia had ever injected drugs, they were never, for the rest of their life, allowed to donate blood. And so we wanted to know, well, okay, what additional risk if we change the policy to say maybe after 1 year, if you haven't injected drugs after 1 year, you can donate blood, or if you haven't injected drugs after 5 years, you can donate blood. But there is actually already a risk, even with the lifetime deferral, there's already risk to the blood supply, and what we call that the residual risk. And that risk is that a person who has ever injected drugs, so say I'm an injecting drug user, I want to give blood, and I just give blood, and I don't disclose the fact that I've given blood. So the additional risk just comes from, if we change the policy, how would that encourage more people who have injected drugs to lie or not disclose their injection? So you can see that laid out more clearly here. So we hypothesized that the additional risk, let's say we change it to a 1 year deferral instead of lifetime, would be that a person who has injected drugs in the past under the new policy becomes eligible because they haven't injected in the past year. And so that's great. They take up blood donation and then relapse and begin injecting again. And then despite returning to active injecting of drugs, they continue to donate blood, because there's already that residual risk that someone doesn't disclose. And so we were trying to think, what is the additional risk of changing the policy? Well, maybe it's that someone becomes eligible, takes up injecting, but then relapses and doesn't disclose. And so this is what we set out to model. The data, this quantitative data, was from injecting drug users in Australia in 2015 and 2016. The Burnett Institute are heavily involved in both of these surveys, the Illicit Drug Reporting System, or IDRS, the Melbourne Injecting Cohort Study, or SuperMix. You can see that IDRX has a number of around 900, and SuperMix around 700 participants. They've been running for a long time. And so obviously getting data from people who inject drugs is not an easy task. And so I think this is a really kind of a good example of how working with an organization that has these programs on the ground that have been running for a long time and are respected in the community really helps you have the data that you need for me to come in sort of at the last minute and get to do this cool analysis. So this is the data that really enabled this work to take place. So as I said, the model's quite simple. We wanted to know the additional risk if we change the referral to 1 year. So we measured that as if the deferral was changed for 1 year, what would the yearly number of collections from hepatitis C window period donation from a new risk group blood donor be? So that's quite a mouthful. I'll just back up and say we modeled the risk only for people with hepatitis C because the risk of hepatitis C is by far the highest risk group amongst people who inject drugs in terms of blood transfusible infections. So we wrote down this model, which is a simple multiplicative model, and we needed to know each of these points. So, okay, how many people in Australia who inject drugs currently don't have hepatitis C? What's the probability that they'll stop injecting drugs for 1 year because that's when they would become eligible to uptake drugs? If that happens, what's the probability of relapse within 1 year as well? Because they need to relapse, as we discussed earlier. And then what's the probability that someone uptakes blood donation amongst the general population? We use the general population because we don't have statistics for what's the uptake of blood donation amongst people who inject drugs after the policy changes. So we just did the best that we could. The Australian blood donor average yearly donations, we know what that is. That's easy. We've got that data. Non-compliance, I'm going to talk about in a minute. That's when someone doesn't comply to the policy that as it exists. So, for example, I would be not complying if I gave blood in Australia because I'm in a risk group and I'm excluded. Yearly incidence of hepatitis C in people who inject drugs, and this hepatitis C window period. So when someone injects drugs, when someone donates blood, that blood is tested for things like HIV and hepatitis C. So if blood is already tested, why do we even have to model this risk? Well, it's because of this thing called the window period. So when someone contracts hepatitis C, there is a period in which it doesn't show up in a test. And so the best test is a nucleic acid test, and there's a window period of 2.6 days. So if I get hepatitis C today and I have this nucleic acid test tomorrow, it won't show up that I have hepatitis C. And so the risk is that someone is in that 2.6 days after they've contracted hepatitis C when they donate the blood. So it's a really small risk, and that's why we did this study. And then on top of that, the yearly risk of someone donating in the window period, because you have to be in the window period, and then you have to donate blood in that window period. So I just wanted to highlight some of the key things in the model. So we've got this non-compliance, which I talked about. So this was really the key piece of data that enabled the study, because this study was commissioned a few years earlier and asking exactly the same question, but the committee, which I wasn't a part of at that time because I wasn't working at Burnett, wasn't able to give any answers because the data wasn't available. There was no information about how often someone who injects drugs donates blood. We just didn't know. And so a question was added to this IDRS and SuperMix surveys exactly so that this study could take place. And so it was, the question that was added was, have you ever donated blood after injecting drugs? And like I said, it was the data that really enabled this study to happen, because then we had a number for the probability of non-compliance. So we knew that number, but without knowing that number, you can't model this probability. You don't have all of the probabilities for the model. And so I know I've said this before, but I think that demonstrates the power of this is a very simple model, but the data that you need, you can't get it unless you're part of this big umbrella of all of these public health organization and then all of these stakeholders. And I was really lucky to just come in, have all of this data available and be able to just work on this simple model. So that's why I wanted to share it today. Okay, so the other piece of key information was this yearly risk of a person who injects drugs donating in the window period. So obviously it's only 2.6 days a year that rewind. So another question that was added to the surveys was, how close to injecting episode have you donated blood? Because unless you've injected and donated blood within 2.6 days, you're not going to be in the window period. So that was also something which we got from the data that was very important. So here are the results that we got from that simple model. That non-disclosure, which was the probability that someone would inject despite the fact that they were in the risk group, was 3.7%. So that was a key piece of information that came out of the data that was collected in those surveys. So there is the current residual risk already, which is 1 in around 11.5 million units of blood which are transfused. And so we calculated the difference, the additional risk for 1 year and 5 years. So if we changed it to, you can donate after 1 year of not injecting and you can donate after 5 years of not injecting. And you can see that the residual risk would be 1 extra infected bag of blood every 815,000 years if we changed it to 1 year deferral, and 1 extra infected hepatitis C bag of blood every 3.1 million years if we changed it to a 5-year deferral. So you can see that this is really negligible risk. And so it's not a fair or reasonable policy to exclude people who inject drugs. Where if we could just change it to be, you can't have injected in a year, you can't have injected in 5 years. So we wanted, I looked at this and I was like, great, we'll recommend a 1 year deferral period. But obviously the people that have been in the space and understand the landscape, which I didn't, were like, no, we have to be very conservative. So what we'll do is we'll recommend a 5-year deferral. So we ended up recommending a 5-year deferral period. And what happened was in September of 2 years ago, so 2017, the blood donation rules for people who inject drugs changed. And so now there's a 5-year deferral period for people who inject drugs. Another thing we did was to model a very conservative case. So some people on the committee said, yes, but what we used the uptake of blood donations amongst the general population. Maybe people who inject drugs will have a higher uptake for some reason. So someone who had kind of a more expert view on that suggested 15% as a reasonable number to choose. And then that non-compliance, we had a lower and upper bound, so we tried an upper bound. So we modeled this really conservative case to be like, okay, in this conservative case, would we still be confident that there's negligible risk posed to the blood supply? And we were, because the additional risk was 1 extra hepatitis C infected collection every 24,500 years. So we were still happy with that. Just wrapping up, in June 2017, we submitted the review to the Australian Blood Bank, recommending that it was negligible risk posed to the blood supply. And then in September 2017, the Australian blood donation policy changed. And we've got a couple of journal articles on the way, which is what reminded me to talk about this work today. And I'm very happy to take any questions.
plasma you can donate every 2 weeks. Not that it changes anything.
Yeah, I think it's whole blood because otherwise, because so for example, if we look at the model here, we've got, I'll just go to this one. We've got the average yearly donation, and I've got some extra slides here. So the yearly donation is 1.8, so that's not going to be plasma. So yeah, it'll be whole. I think we model whole blood. That's a really good question. I don't work at Burnett anymore. I'd be surprised if they weren't. But then maybe I maybe I actually wouldn't be that surprised because we all know how hard it is to get data, even though you'd think that collecting it would have been obvious. Yeah, that's a really good question. I don't know the answer to that. Yep, at the back. Oh, so like collect a bag of blood. Yeah, I don't know. Maybe.
I think the risk would be that the shelf life is not.
Yeah, maybe it doesn't last that long because we had. I'm not a blood expert, but we were working with people who were, and I feel that that must have occurred to someone. So yeah. Yeah, Paula? No, I mean, we know how many people, so let's see, annual hepatitis. Okay, so estimated people who inject drugs in Australia, 93,000. So, no, because what happens is when you go to give blood, you arrive, they ask you some questions, and then if you don't, then you just walk away if you didn't fit the policy, and I don't think that that's recorded. Yeah. It's no, the drive to do the project from the blood bank side was just that it's discriminatory. So they just need to not have policies that discriminate unnecessarily. Yeah. Yeah. I don't know. I think my group at some point worked on looking at the risk of, for example, men who have sex with men and the HIV risk, which is the main risk for that group. And my intuition is that that's a discriminatory policy, but which probably also hasn't been looked at since the 80s, but reasonably enough when it was made. But I don't know what the answer is, but I know that people have looked into that, and I know that there are this type of work as well on looking at whether or not policies are reasonable and fair has been done not just in Australia. It's done because obviously there's different amounts of risk in different countries. So I think Canada's another country that's done similar things. So I don't know what the answer is, but I have this inkling that there was a study in Canada that studied that particular risk group. Yeah. Yeah. Oh, yeah. I meant to say. Yeah, well, that's one thing I learned about public health is that you just take what you can and do your best, and that's one of the reasons we modelled the conservative scenarios. So all of these probabilities were taken from either the Australian Blood Bank actual numbers, or probabilities that came, and there's no errors in the amount of donations, that's very well known, but for example, probability of relapse, we just take that from the best published study. And my colleague, I just had to trust that my colleagues are across that research enough to take the best possible, the most representative probability that we have for Australia, and that we could we tried a lot of different. So the final results show the 95% confidence from like modeling all the ranges of each of these probabilities, but we tried a lot. So we tried a lot of worst case scenarios, and were confident that even in the worst case scenario, there was negligible risk. Yeah. Cool. Any more questions? All right. Thanks again, and feel free to come and chat to me or Fatia about Young Women Leaders in AI Camp.